Is that on? Yeah. Okay, great. Okay. Hi everyone, I'm Camille, and I will be presenting a work in progress, which is loop saturation for scalable HLS. And this is a joint work with my advisor, Qirun Zhang, and Professor Callie, and we are all at Georgia Tech. So I will try not to do too much repeating of what's already been said, but I'll give a little bit of background on EGRAPHS and HLS, and then the motivation of this particular line of work, the approach, and some preliminary implementation and results, and then finally the limitations, the current state, and conclusions of this experiment. So first of all, obviously, okay, we don't really need this slide, but EGRAPHS, considered, for me, in this application, they're a compact representation of many equivalent forms of a program. So we have our little canonical example, x times 2 and x left shift by 1. So E nodes are in solid lines, and then the E classes are in the dotted lines. E classes contain E nodes that represent the same expression, etc., etc. Edges are always from an E node to an E class. Okay. And then equality saturation, you iteratively apply, rewrite rules until you can't anymore. Okay, so now also a bit of a repeat, but we have some background on high-level synthesis. So we have hardware description languages like VHDL and Verilog, which are used for programming firmware as well as hardware design for ASICs. And this outputs RTL designs, but this is time-consuming and error-prone, and it requires someone to be somewhat of an expert in writing in these hardware description languages. So wouldn't it be nice if we had a tool to go from a higher-level language like C, in this context I guess C is a high-level language, and take it to the RTL design. So that's exactly what HLS does. It takes C code and outputs a hardware design. And one sort of unique thing about HLS is that it uses the source code structure to guide the structure of the output design. And that is different from what we expect of a compiler, which is sort of supposed to take no matter what source code and optimize for the CPU, whereas HLS sort of reads into that design, the code format a little bit more to try and extract design information. And that can be a good thing, but also a bad thing. So this is an example. These are two pieces of code. They are equivalent. One of them is just an unrolled version of the other. So here we have just sort of esoteric piece of code that does a bunch of array operations, and then the looped version of that same thing. And I want to explain how HLS will treat these two pieces of code and why that might be a problem. So here we have this piece of code, and HLS will try to parallelize as much as possible given the correct array partitioning. So here we have these 4 operations that can all be done in parallel. And to all the hardware people, I'm going to be calling things clock cycles that are not clock cycles, so I apologize. But at a high level, we'll just say that each of these operations is 1 cycle. And they can all be done in parallel, so HLS will say, great, I'll make hardware to do 4 things at once. And then same thing for the next set. The next 4 operations have a sequential dependency with the preceding operation, so they can't be done all in one, but this will result in a 2 clock cycle or abstracted clock cycle implementation. And that's great if you want to go fast, but those operations or this implementation will use a lot of resources or more hardware resources. So doing things in parallel means actually having hardware to do many things at once, which means copies of the same circuit. So on the other hand, we have this for loop implementation, and if you don't tell HLS to do anything, it takes this for loop and treats it as a design specification. So it says, okay, the internal body of the for loop is 1 piece of hardware, and we will use that 4 times. So the way that this gets scheduled is these operations happen in sequence instead of in 1 or in 2 parallel cycles. And this is just sort of the sequences of the different loop iterations. So that will take 8 cycles, And then, yeah, here we have a slower implementation, but on the other hand, hardware-wise, things are reused. So there's an internal circuit that is passed with different arguments each time instead of having parallel things happening, which means bigger circuits. And then I want to go into a middle ground example. So HLS has these, or supports these things called pragmas. You insert them into the C code and they tell HLS how to treat certain things. So we talked a little bit about pipelining and unrolling before, but I just want to show why loops can be sort of a middle ground for HLS given the existence of these pragmas. So here we insert a pipeline pragma, and what that tells HLS to do is see if it can start the next iteration before the first one has finished. So if we take our two operations again, we'll start and HLS will schedule them in sequence, but then it checks at the second clock cycle, can I actually use the hardware from the first instruction and schedule the next iteration at the same time as the second half of the first iteration? And it can in this case, so it will try to do that, and that way save on clock cycles. So propagating that through, we end up with a 5 clock cycle implementation, which is of course slower than the fully parallel, but a middle ground between that and the fully sequential implementation of the same code. So all of that to say that basically HLS will use your source code structure to generate, to choose what hardware format it generates, and that may be a problem if you have resource constraints. So you may be running on, let's say, an FPGA that has limited LUTs or functional units, and then also domain space exploration, as mentioned before for HLS, is often done in the direction of improving latency, maybe improving latency while conserving area, but rarely going in the opposite direction. And so that can be an important direction if you want to really explore all the possible optimization directions. And then the final thing is that when you take in C code is typically optimized for CPUs. So if we want HLS to be a tool that just takes C code and outputs the best, hardware, then we need to go in a bit of an opposite direction and assume that it was not written for HLS with HLS in mind. So the key insight is that software loops represent scaling and reduced resource utilization in the HLS world. And because EGRAPHS and equality saturation are great for source-to-source rewrites, the idea is maybe we can use EGRAPHS at the C code level and do a source-to-source transformation and end up with a better scaled output for HLS. So this is the case study that we've started implementing on. This is, I just want to explain what kind of code we're working with to explain why this works. So this is, we work on fiat cryptography, which is a repository, well, it's a project which consists of formally verified cryptographic primitives. And this is a set of generated C source code, and it's generated from it's automatically generated from proofs in Coq that prove that the primitives are correct. And the output of this is straight line C code. And the goal of this project was to have performance that compared with manually implemented C code. And these are useful because they're auto-generated, so they have a lot of patterns that are useful for looping. And also, cryptographic applications are often deployed in resource-constrained environments, so this seemed like a relevant case study to apply this approach on. So we have 4 sections to loop saturation, which is what I'm going to call equality saturation for loops. There's array injection, IR detection, loop rerolling, and code extraction. So array injection is basically just handling this problem here. So we have on the left the ideal code format where everything is indexed with a, or everything is an array index. And then on the right we have a more realistic situation where there are a bunch of local variables that make it hard to infer a loop structure. So how do we get from the right to the left? So the first step is to replace these local variables with arrays, and we can do that by analyzing data dependencies in the source code to map variables to array slots, and basically replace local variable definitions with arrays. So of course this is assuming that the types work out. And then looking at the source code, we can assign concrete index values to those array indices. So here we have an example. Looking at these local variables and how they're used later on, we can sort of map them to indices in a local array instead. And we can choose that those like index bins based on where the local variable is used. And then we can assign indices to those bins based on the access patterns of the other arrays in the rest of the code. So the next thing is IR detection. Basically, this comes down to the fact that ASTs are large and bulky and complicated and sort of unnecessarily complicated for this case study. So we look for program portions that only that don't have local variables, basically. They have local variables that are in the form of indexed arrays. And once we have pieces of code like that, we do pattern matching. So look for patterns that can be abstracted where the holes are just integers. And those integers can be array indices or constants, but basically no local variables. So here we have a bunch of code that has the same pattern over and over. And so we can take that pattern and abstract it into this operation. That's pretty simple. So straightforward enough, basically just take the code on the left and create the set of operations on the right. And this will make it easier to do eGraph transformations later. So the next thing, actually similarly to SEER, we have the sequence operator to indicate that things are meant to be done in a certain order. And then we have rewrite rules based on the source code. So that can be depending on data dependence information. So do we know if instructions can be reordered or not? And then also guessing what kind of loop steps we'll see based on the array access patterns in the source code. So again, this is the same example, but with that sequence operator generated, and this is like the first eGraph, so no rewrites are applied yet, and it's just a sequence of abstracted operations. And then here are two example rewrite rules, which I'm going to apply in the next couple slides, but first we need to figure out how to get loops from the straight line code, and then how to actually combine instructions into larger loops once we've injected one. So I'm going to zoom in on this part of the eGraph just because otherwise it would make a very large diagram. So taking this sequence of operations, first we want to figure out how to inject a loop. And we'll do this by applying the rewrite rule from earlier. And these are just sort of unit loops. They don't do much. They just loop around one operation. But the important thing is they inject that loop variable into the abstracted operation. And then the next thing is to figure out how to get those loops to be more than just unitary. So this is the loop osmosis rule, and this rule takes a sequence of a loop and a different operator. And looking inside of the loop, we can see that that abstracted operation on the right-hand side can actually be consumed by the loop on the left if we just change the loop bounds. So the only difference is that we need to do one other thing. Or we need to start I one index earlier. And so then we end up with this rewrite. So it's applied to the sequence operator, and it creates a new enode in that E class, which is a for loop over those two sequential operations. Okay, and then next, finally, we need to extract the final loop structure from this example. So currently we use AST size as the extraction metric because that correlates with the most loop version of the code. of course, I think ideally we could have, well, we'll go into the future work later, but having an HLS-based cost model would be ideal here. But at the moment, this works. And so we extract basically the shortest loop possible, so consumes as many operations as possible. And then here the translation process is pretty simple. Oops. Remembering the abstracted operation from earlier, we just take the loop bounds from the eGraph and then rewrite that operation into the C code that we pattern matched. So the implementation is currently very simple. It's in Python for the array injection and IR detection. And then once we have an eGraph structure that's amenable to egg, we use egg to do the loop saturation and apply the rewrite rules. So again, we're applying this to fiat cryptography, which is a set of auto-generated C code for cryptographic primitives. And we look for loop structures in that code. And then we say that this is an important application domain since cryptography is sort of needed everywhere, so resource constraints may apply for different use cases. So here are three of the three examples where we ran this approach, and we ended up with 3 looped versions of the original straight line codes from Fiat. So these are 3 different or 3 different parts of cryptographic primitives for 3 different elliptic curve cryptography programs. So we can see that performance does take a hit, but we're going completely in the opposite direction. So we're just optimizing or we're just trying to figure out how to get the best area here. So we take a hit to performance, but you can see that the hit to performance is not sort of a linear function compared to the hit to the area. So the area optimization is much more intense than the sort of performance degradation. And so, yeah, we can see that this is a useful approach if you are trying to run on constrained hardware or have area constraints on the chip that you're designing. So again, obviously there's a lot of limitations. So currently we're relying on patterns in the source code. That's fine for auto-generated code, but it's obviously less predictable for handwritten code. And then of course choosing rewrite rules is non-trivial. So we assume that loop steps is affine. I think someone mentioned that earlier. But in practice, things can be more complicated. So basically we apply, or there needs to be more work on how to generalize this approach to other C programs. So in conclusion, as we've said before, HLS and CPU optimizations are very different, and C code is usually written with CPUs in mind. And so if we want HLS to take any C code and output the best possible hardware for whatever constraints we give it, we need to be able to move in all directions. So optimize for both size and latency, depending on what the designer wants. And using EGRAPHS, we can discover possible loop structures, which represent a size optimization of the chip. So finally, this approach can help discover more space-efficient implementations for the same circuit and improve design space exploration in general. So yeah, that's the talk, and I'll be happy to take questions.
All right, thank you. We have time for a few questions.
So if you go back a few slides, you had the example where you actually replaced the left-hand sides of assignments with the actual right array index. A little bit before.
Oh, yeah.
Yeah, where you have the variables and then you change them with the indexes. So yeah, there. Yeah. Do you think that some sort of like point-free approach with no variables is possible? So where you just have a graph and you just check the flow of stuff where it's going without using variable names? Before you do
Yeah, I think that is possible. Like you're just saying, look at the dependence graph and figure out where things are used and then
Yeah, because it seems like the hypergraphs stuff from this morning would be very cool for this kind of
Yes,
stuff.
yeah, that is true.
Yeah, thanks for the great talk, first of all. There was one slide where you mentioned loop osmosis and the other thing, and I want to talk about the other thing. So there was this base case, basically, where you had op0, right. I want to understand kind of what things is this able to understand from what kind of pattern. If you just have two inputs, like what can it understand and how does this person actually work?
So I guess it's looking at the it takes the important thing is the loop variable, and you check basically given the step, can we go by going one step further in one direction, can we include the neighboring operation? So like if we look at like replacing, if we start with I equals 1, if we go one step backwards, so by adding the step to 1, can we, are we obtaining the operation that is next to it? So the important thing here is like I1 minus minus, right? So you're adding that and you're saying, like in the rewrite rule in egg, you would say like, okay, if I take the bound on the loop, so I equals 1, and then plus the step, is the operation next to it equal to bound plus step? And then if yes, then you can just decrease or like add the step to that bound, and now you have subsumed the two things. Does that make sense? Okay.
Do you think this is going to be really tricky to extend to things like nested loops and trying to kind of infer the structure of like array accesses from just like two examples, for example?
So nested loops is not as bad as you might think, because you can sort of treat the loops as their own operations, and then do the same thing just on a higher level. So instead of the abstracted operation here, you would have loops, and then you look at how the bounds progress. The tricky thing is that the bounds need to work out. So if the bounds don't work out, then things get uglier, and you might end up with like weird loop structures you didn't expect to see because instructions get reordered. But yeah, nested loops are not as difficult as you might think. But what was the second part of your question? Sorry. Oh, yes. Conditionals, definitely. So currently on straight line code, basically I'm just taking pieces of code that are straight line and then applying this to them. But for conditionals and branching and stuff, yes, this will be more complicated.
Okay, thanks so much.
Cool,
Let's thank the speaker one more time.